Well, let's start this last session, this afternoon session. We will start with Victor Martin Lozano. Well, neutrinos driving the standard model to the swamp plan.
Hi, everybody. I want to thank the organizers because they invited me here, and it's a nice city, a nice conference. And I hope you could enjoy my talk. So this is work done with Luis Ibáñez and Irene Valenzuela. And the title, if you don't know what's the swampland, could be a bit confusing, but I will try to explain what's that. So if we have a look at the physics that we know, we can just put a line of energy and we can just set all the scales that we know, or all the scales and effects that we know in physics, from the Planck scale to the neutrino scale. And if we set such line, we can have two natural problems, two natural questions, that are the cosmological constant and the electroweak scale, right? We don't know why the electroweak scale and the cosmological constant have these values that we see in nature, and we try to answer these questions. So for the electroweak scale, we have the LHC. In the past, we thought that the LHC could solve this problem, or at least shed some light. But unfortunately, we haven't found anything but the Higgs so far. We don't know if there is something that will come in the next years, but still we don't know, and we don't know the answer to this question. So we have to look at all the scales. For example, this is just a numerical coincidence that could be just by accident. If we compare the mass of the scale of the neutrinos and the cosmological constant, we see that they are somehow related. Okay, you can say that this is just a numerical coincidence, that it is. But this could make us think that the absence of new physics forces us to think differently about the guiding principles of high-energy physics. So maybe the ultraviolet structure, what is happening here, is telling us how the infrared physics here should behave. So in that sense, these two quantities could be related. So if we want the ultraviolet structure to tell us something about the infrared, we should use what they are called quantum gravity constraints. So quantum gravity constraints, what are those? Well, not everything is possible within string theory or quantum gravity. This is something that, in principle, we have been told that it is the other way around, that if you have a string theory, you can construct every model. But Baffa in 2006 came up with this swampland conjecture that said that not every effective theory can be embedded in quantum gravity. If we think in all the effective theories that we can have, some of them would not have an ultraviolet completion. And we represent this as the swampland and the landscape. So these blue things are the effective theories, and only some of them will have an ultraviolet completion. The ones that have an ultraviolet description lie in the landscape, while the others are just stuck in the swampland. So this is the swampland. All the theories that cannot have an ultraviolet description. This is how string theorists see the swampland, but maybe people in Valencia see the swampland like this. This is La Albufera. So move on with this. The quantum gravity conjectures, yes?
That means that we no longer look for the theory of everything. You look for the theory of something only. The rest is the swampland.
Yes, I mean, the thing is that not every effective theory could come from an ultraviolet theory, basically. So these quantum gravity conjectures are guiding principles to build an effective theory that is consistent with quantum gravity. So these usually are common features on the string landscape or just model building failures, so you know how not to do things, and black hole arguments. And for example, we know some of them, the absence of global symmetries. They should all be gauged. And well, we have the completeness hypothesis, the weak gravity conjecture, and swampland constraints about the modular space. We are going to work with the weak gravity one. And we are going to see that these conjectures could have a significant impact in low energy physics, something that in principle we don't expect. So what is the weak gravity conjecture? Well, it's really simple. It is telling us that gravity is the weakest force. Okay? If we have, for example, a gauge field, there must be a particle that is charged under this gauge field, and its mass has to be less than the product of the Planck mass and the charge of this particle. This is usually done in order to avoid remnants of black holes, because they would form bound states. So the statement is clear. Gravity must be always the weakest force. Then Oguri and Baffa came up with a sharpened version that if you develop this a bit more, it tells us that non-SUSY ADS vacua cannot be consistent with quantum gravity. So once we have a theory that is non-supersymmetric and we develop an anti-de Sitter vacuum, then our theory is in the swampland. It is not consistent with quantum gravity. But if we have a consistent theory, it is consistent in any background. And this means that if, for example, we have the standard model and is consistent with quantum gravity, any compactification of the standard model should be consistent. And this is where we are going to play. We are going to compactify the standard model and see if the standard model develops ADS vacua. So the standard model shouldn't have any ADS, stable ADS, lower dimensional vacua. So let's take the standard model and gravity, and let's compactify one of the dimensions in a circle. The potential that we have in terms of the radius of the circle, we will have different components. The first one is the one due to the cosmological constant, and then we have the Casimir energy. There are one-loop corrections, and all the particles in the standard model will contribute to this Casimir energy. These one-loop corrections are proportional to this negative exponential, and we see that for high masses, the contribution is really low. So we are going to play with the light mass spectra and the cosmological constant to see how we can get this ADS vacua. So if we have a look only to the contribution of the cosmological constant and the one coming from the graviton and the photon, we see that this red curve is the potential with these two contributions. So the graviton and the photon are bosons, so their contribution is negative according to this Casimir energy. And what we see is that when we go to radius next to 0, the potential just goes down, and it is not bounded from below. So if we go further in energies in masses, the next thing we find is the neutrinos. And their contribution is this. As they are fermions, according to how we define the compactification, the contribution is negative. And well, it depends on this function that is described as some more complicated functions. But usually, if you take the first terms, they are really similar to these ones. So the next contribution from the neutrinos would be some mass term that has negative sign. But the main term is positive. So what really matters now, it's the number of degrees of freedom. So having this potential, we can see that we will have, well, a cancellation between these two terms when this number of degrees of freedom is just the same as the one of the graviton and photon. So, well, we are going to test this in the neutrino sector. So we are taking into account the two hierarchies, and we are going to vary the mass of the lightest neutrino. And once we fix the value of the lightest neutrino, and we choose one of these two hierarchies, all the rest of the masses are fixed. So let's try with Majorana neutrinos. So we are here in one radio, and when we approach smaller radius, more or less of the mass of the lightest neutrino, that is 0 in this case, the contribution of this neutrino is to the number of degrees of freedom is 2, so it's +2 - 4. Still, this term wins, so the potential goes down until we reach the masses of the rest of neutrinos. So now we have 6 degrees of freedom, so 6 - 4 is 2, and the potential goes up. So a minimum is developed here, and as the potential is negative in this minimum, we get an ADS vacuum. So if we increase the mass of the neutrinos, as the next term is negative, what this is going to do is just to develop a deeper minimum. What this is telling us is that for every mass of the Majorana neutrinos, we develop always an ADS vacuum. If we go to the Dirac neutrinos, we have more degrees of freedom. So in the first case, when we have the lightest neutrino massless, we don't develop any ADS vacuum. So if we increase the mass, this is the meaning of the different colors, we make the minimum deeper until we reach negative values of the potential. In that moment is when we develop the ADS vacuum, and the model is ruled out. So we can put a constraint on the mass of the lightest neutrino with this. So with this, we realize that Majorana neutrinos, only the standard model plus gravity, if we only have Majorana neutrinos, we develop always an ADS vacuum. That means that the standard model plus gravity is in the swampland. It is ruled out, basically. So we should find something to avoid that. This could be a hint that if we take only the standard model, the nature of the neutrinos is Dirac. So if we see the Dirac case, what we see is that there are some upper bounds on the mass of the lightest neutrino. So the lightest neutrino for normal hierarchy should be less than 7.7 MeV, milli-electron volts. And in the case of inverse hierarchy, the bound is lower, and it's 2.56. Having this, we can check what happens if we vary the cosmological constant. So if we vary the cosmological constant and the mass of the lightest neutrino, we obtain this parameter space in green that is allowed because we don't get any ADS vacuum. And if we interpolate this curve, we obtain this formula. And what it is telling us is that the cosmological constant depends basically on the mass of the neutrinos to the fourth. And this is the explanation why we obtain this at the beginning, this numerical coincidence. Well, but apart from that, this is the first argument, as this is greater or equal than this, that only depends on the mass of the neutrinos, and we know that the neutrinos are not massless, they have mass. It's the first argument in particle physics that tells us that the cosmological constant is not 0. So basically all the arguments to say that the cosmological constant is not 0 came from cosmology. But this one is the only one coming from particle physics. But what happens now if we go further and we take more than the standard model? What happens if we add a Weyl fermion? Well, if we include a Weyl fermion in the setup with Majorana neutrinos, we can see that there is a region in the parameter space for some masses of this Weyl fermion that we are adding that now we don't develop this ADS vacuum. So for masses that are more or less in the same range as the neutrino masses, we can save the standard model and we don't develop an ADS vacuum. So the only way to save Majorana neutrinos in the standard model is adding a light Weyl fermion. In the case of Dirac neutrinos, the only thing that these Weyl fermion are doing is just to make bigger the allowed parameter space. You can see the king here. This is when the mass of the light Weyl fermion approaches the mass of the neutrinos. Yes? It is just a Weyl fermion. So you can
could be the lightest of the three neutrinos if they are normal ordering.
Yes. So the thing is that here it doesn't matter how it is connected to the standard model. If it is connected to gravity, it will generate the Casimir potential.
It's an extra.
Yes.
It has to be extra to the three that we know.
Exactly. But it could be a neutrino or something that you call Weyl fermion.
But of that mass and unspecified gauge couplings.
Exactly. Because you don't have to specify how is your gauge content or the connection to the standard model, because this is generated only by gravity, by Casimir, is the Casimir energy, is loop corrections to that. So this, for example, if you consider that this could be the dark matter, it would be the dark matter, or some extra neutrino, this could be the same. Sorry? Yes. Okay, in order to connect, you mean with the standard? Yeah, okay, yes. Yes. So if we have the Dirac fermion case, as the Dirac fermion has 2 more degrees of freedom than the Weyl one, the area that is now allowed is greater, and the only bound that we have to confront is the absolute, the sum of the masses of the neutrinos coming from Planck. And in the case of the Dirac neutrinos, the area is again bigger. So you may think, okay, these are conjectures, you are playing around, you are taking something that is not really robust. But at the end of the day, what we know about the standard model is that we are in the de Sitter vacuum. So we are here, and maybe there could be another deeper vacuum that could be ADS. So the standard model could be in the swampland, and the only way to avoid it is maybe new physics that we haven't seen. Yeah, sure, I mean, this is a conjecture, of course. But well, I just come to the conclusions. Not every effective theory can be embedded into quantum gravity. And we follow these quantum gravity conjectures to build effective theories that are in accordance to quantum gravity. And consistency with quantum gravity implies constraints on low energy physics. So the way we construct our theories in the ultraviolet will affect to the neutrino physics, as we have seen. And when we take ADS instability conjecture plus stability of three-dimensional standard model vacua, we set a lower bound on the cosmological constant and an upper bound on neutrino masses. And also, we saw that BSM physics can save some scenarios. And that's everything.
Thank you very much, Victor. Are there some questions or comments?
So imagine that tomorrow you find that what happens to these conjectures in this one land stuff.
Well, for me, if, as we saw, Majorana neutrinos are ruled out. So if we see double beta decay, and this indicates that we have Majorana neutrinos, for me, what it is telling me is that we should have new physics around, because it's the only way we can have Majorana neutrinos in the standard model. It is true that this is only for non-SUSY vacua. So when you have a supersymmetric theory, this doesn't hold like this.
So I guess you can also generate the neutrino, Majorana neutrino mass without adding extra signals.
This, okay, but then if you generate this with, for example, a singlet or, well, something that acquires... Okay.
But would escape.
No, that will not escape because you are adding scalars and scalars don't matter.
The thing is that you should go to low masses. So if you have scalars, they will contribute in another way. Okay, because as they are scalars, they are bosons. And if we go here, bosons contribute with negative energy. So what happened there? You are making deeper this thing. It's like if you add actions. But in that case, there is a number of bosons that you can add in such a way that your minimum goes so deep that it breaks and it is not bounded from below. And in that case, you don't have any vacuum. So in principle, this conjecture will not hold in that case.
But you could add more scalars, keeping this minimum shape. Why not?
Yes.
But you don't want minima because the minima is a danger part.
Exactly. So the thing is that
You want to avoid minima.
you want to avoid minima that are below zero.
Okay. But you can always play with the degrees of freedom and obtain solutions for these in a multitude of ways.
So what he is basically saying
Not only by Fermi.
No, of course.
What he is basically saying is either if you want Majorana neutrinos, then probably there are more sterile states.
Mm-hmm.
There are more sterile states, or maybe neutrinos are derived.
Exactly.
So you can have Majorana neutrinos, but then you have to live with several sterile neutrinos also.
Yeah, and they have to be...
You have to choose which is the bigger available.
But there are
A
other
lot of
solutions.
sterile states.
How about having only scalars?
So
Yeah, but if they are heavy, you cannot...
absolute opposite. So they make
Exactly.
the problem worse.
And if they are too heavy, they don't contribute to this, because their contribution is
You have no room
like this.
Okay. So we must play only with Fermis.
It's kind of opposite of vacuum stability, right?
But it's opposite. Yeah.
Yes. So you keep on adding Fermi.
Exactly.
you make the problem worse.
There, scalars solve
Yeah,
the
the
problem.
scalars solve the
Here
problem.
they worsen.
Yes.
Well, it is.
I'm not sure if I understood your argument in the last slide before last slide, when you say that the standard model is a metastable.
Yeah?
Okay. So I mean these plots were done assuming there is no other physics from the electrolyte scale up to the Planck scale.
Yes.
So I mean, and we know that probably this is not the case for many reasons. So saying that the standard model is in the swampland based on these plots, I think it's a bit because
It may be.
you just add Dirac couplings, for instance, with a singlet neutrinos to explain neutrino masses, and this picture changes.
Sure, but...
Any model with dynamical mass generation for neutrinos automatically solve this problem. Not all the times, but let's say half of the solutions solve the problem.
But what I'm saying is the standard model is in the swampland. The standard model
Standard model
doesn't...
is rolled out because there are no neutrino masses. We have to get used. The standard model is rolled out. No physics has been found already. But we don't understand.
Once you include neutrinos in the standard model, you cannot show this picture.
Okay.
No, I disagree.
Well, I mean, yeah, I mean, if the
I will include this.
No, I disagree because they said that if the states are very massive, it doesn't matter. So only light states matter. So either you change the picture by adding light striles or going to Dirac neutrinos. for vacuum stability, light strikes or Dirac neutrons doesn't really matter if there is no mass mechanism behind it.
Yeah.
So the vacuum stability, if you just have Dirac neutrons with small Yukawas, this picture doesn't change.
Yes.
For the vacuum stability. But the swampland picture changes.
Yes.
Exactly.
That's the difference.
Thank you, Victoria.
Thank you.
So we now have Javier to talk about dynamical generation of fermion masses in warp dimension.
Okay. Thanks, and thanks to the organizer for the nice workshop. Yes, he said I'm gonna talk about a mechanism for dynamically generate fermion masses on warp extra dimensions. I did this in Mainz with my collaborators over here. Okay, first let me just motivate the model. Okay, like we know, it has been discussed here in this workshop already, that one of the most intriguing puzzles we have in the standard model is its flavor structure, like why the hierarchy is in the masses and why the mixins. And one solution for this would be warp extra dimensions. Like this problem is solved quite naturally there. In warp extra dimensions, this is solved by the localization of the fermions along the extra dimensions. And but let me tell you first what extra dimensions, warp extra dimensions are. Warp extra dimensions were introduced by Randall and Sundrum in 1999. And it was first introduced to solve the hierarchy problem. But also you could realize that, as I'm going to show on the next slide, that you could also solve the flavor puzzle there. But okay, what's warp extra dimensions? Warp extra dimensions are defined by this metric over here, and it allows you, by an exponential metric, to, if you have a mass scale in your theory, just by the warp of the metric, to get an effective mass scale. An effective mass scale on, for example, here we are going to do it on the other brane. So you get if you work with, if your only scale is Planck scale, you will have on the infrared brane, you will have we assume we have on the IR brane a scale order TB. Okay, what's going to be the geometry we assume for the extra dimension? We're going to work with orbifolds, as we should all know about orbifolds, thanks to Michael's talk. But since we're going to work with only one extra dimension, we're going to assume this orbifolding here is SU1 mod Z2, so we have this transformation for the fields. And then this allows us to introduce, in this case, our 5D fermions would be vector-like, because now the gamma 5 is introduced, is part of our Clifford algebra. And then we can define, this is quite common, we define this C parameter to be the mass of the fermion in units of the curvature. So this mass term is now allowed. Now we use this KK decomposition, and what we do is we can associate chirality with the set to parity of our fields, and then this allows us to, from the 5D vector-like theory, to go to an effective chiral theory in 4 dimensions. Then this C parameter, as I told you about, is now fixing the localization of the fermions on the extra dimension. And if for the zero modes, those will be the fermion zero modes will be our standard model fermions. And just localization will, if we set the Higgs to be on the IR brane, this localization is what is giving the mass to the fermions. So just by small changes on this C parameter, we could explain the whole, we could get the whole hierarchy in the fermion masses just by small changes on C. But
give a geometrical description.
Yeah.
But this is far from being a solution. This is just a picture. Yes.
Well, yeah. Okay, but now there is one thing we need to take into account, if we use this decomposition, now this fermion bilinear needs to be odd. Because we want to associate chirality with this set two transformation, so if we want to have like a left-right bilinear, that will be odd. So what we can do? Usually the most common approach used on the bibliography is, okay, we stick a sine function next to the mass term, and we're happy. But then, let's say, why don't we try to generate this dynamically? Then what we're going to do is we're going to introduce a new Yukawa term with, this is going to be a scalar that is odd on the extra dimension. And this was in fact proposed by George at the beginning of the century, but for a flat extra dimension. So now it gets now a bit more complicated. So this is going to be the model. We introduce this action here with this potential that's going to induce a spontaneous symmetry breaking on the bulk for the scalar. And we're going to use the BEF of the scalar to be the mass of the fermions with the Yukawa term. And also we're going to consider the coupling to gravity. We could do this without considering back reaction, but we're going to use it just to see how it changes the metric, if it's consistent or not. So those are the equations of motions we get. This is the mass of the scalar, over m Planck in 5 dimensions. This would be like the coupling to gravity we have. And this here would be the dimensionless mass for the scalar. And here, this is without back reaction, that would be like Kr usually in Randall-Sundrum, but we could also set it to 0 if we work on a flat extra dimension. And these here are our boundary conditions, so we need the BEF to vanish on the branes, so this is odd. And those are the solutions. Usually, this here in green would be the Randall-Sundrum solution, the sine function, and this is what we get dynamically. I'm going to explain in a while we use these 13 TBs for the mass of the first gluon Keke mode. And yeah, this is a picture of what we get for different masses, and with a small back reaction, that would be the dashed lines, but we don't see pretty well because we're fitting the same gluon mass, and in fact, this collapses the solutions. So for those who have worked with Randall-Sundrum, let me tell that now MKK loses kind of all meanings, because since the metric is changing for our model, even if you use MKK as a benchmark point to compare, then we will get, if we fix MKK, we will get the masses for all of the gauge bosons, for example, completely different. So we just get the first KK mode for the gluon to be like, to compare models, to compare solutions. So this is the solution we get for the metric. In green, we will have what's the Randall-Sundrum for this mass of the first gluon. And as we'll see, the metric goes, we get to higher values for the metric on the AR brane. This is also good because this allows to solve what is called this small hierarchy problem, in the sense that if we usually get to order TB on the infrared brane, but you don't know how to explain why you have TB and you get still a Higgs mass of 125 GeVs. So this could help here. And now, okay, why are we choosing 13 TBs for the gluon mass? Those are the updated figures for S and T parameters. And we got now the ellipse has tilted a bit and have been reduced. So now we find that this would be the minimal case, this would be the custodial case for some back reaction, no back reaction here. And these triangles here, I'm showing just the Randall-Sundrum, minimal Randall-Sundrum model. And this here is what we get with the scalar.
What is in G?
Yeah, the minimum mass allowed with 2 sigma for the gluon.
For the glue?
For the first KK gluon. So actually we see that now for the custodial case, this is worse. It's getting worse because the ellipsis has tilted a bit. But also we should know that this is not as bad as it looks like, because this point over here that are pretty close are order 7, 8 TBs, and we know that the top contribution to this to this curve makes it go high here.
So I think I'm missing something. You're talking about the mass of the glue.
Yeah.
First,
yeah.
sector.
Sorry.
Okay.
Yeah. The first KK mode.
Tower.
Yeah.
Tower.
The first one. Yeah. And yeah, sorry, let me say that this all has been computed only using the metric. So this is the first order on V over MKK. So that's why I'm not considering the top.
The other is the massless sector.
Yeah, exactly. So yeah, so I'm gonna use now only like 13 TVs. That's why I'm using 13 TVs for all the pictures, for all the plots. But yeah, like we could easily here get points into the ellipses once we consider the first order on V over MKK contributions.
But this is a Randall-Sundrum scenario, not flat extra dimension.
Randall-Sundrum, yeah.
This is flat?
No, Randall-Sundrum. Yeah. Randall-Sundrum, and this is with back reaction by the scalar, and this is no back reaction. Yeah, so I'm showing this for 25 for a dimensionless mass, order 25. Like this, we have some requirements that it should be at least of this order, because otherwise you don't spontaneously break the symmetry for the scalar, so you don't develop a BEF. But like we have also like plot for higher values, and we get that the minimum mass we find for the gluon decreases a bit, but this is just a benchmark point. But then also, now you could say, like, what about the scalar? Are you going to do some pheno based on the scalar, like some direct searches or something? Actually, we won't, because we computed the masses for the scalar for all these cases, and we find this, at least, it will have to be like order 1.5, the mass of the gluon. So this is far, like, you will never see it on a collider at the stage we're now. So no pheno for the scalar, but this is more interesting, I think. Like, as I was telling you, what the masses you get for the fermions are those, like, it depends on the localization you have for the fermions on the 5th dimension. And then, like, what you have is, you will have a Yukawa. What you assume is you have a Yukawa of the Higgs with the fermions. You assume this Yukawa to be order 1. And then this is a function, this just like the profile of the fermions times a constant. And then, like, these profiles is what gives you the effective Yukawa. So this is what you see in the standard model. And here what I'm doing is I'm fitting the 5D profiles of the fermions to the same F, okay, to compare. And we can see, like, this in green would be the Randall-Sundrum case. Now, if we consider the scalar with a back reaction and the scalar with back reaction, we see that the profile is more peaked toward the IR brain here. And here we don't see really much difference. So this will affect on the phenomenology, because now every time you want to compute an observable in 4 dimensions, an effective observable, what you have to do is you need to integrate out this 5D profile. And now the contribution of these guys here, because they are like weight by the metric, is going to be lower, as I'm going to show you now. For example, we did this with for epsilon k, which is one of the biggest constraints we have on this kind of models. And this is what we compute. This would be the Randall-Sundrum case. This is now the uncertainty we have now on epsilon k. And let me say that I'm doing this for one Yukawa that we generate randomly, but we could do this again and again just by a random scan. And you can see that now the profile of the fermions, because it's like, as I was saying here, they decrease. You get like more relaxed contributions to epsilon k because of the coming from the fermion KK modes. So sorry, here those are the relevant operators. Here in this section, the most important operators would be like Q4, Q5. Those here, the mixed terms. And here what you have is the left-handed modes contribute really hard to it, and here the right-handed modes, because of, like, sorry, this is the left-handed F for the left-handed fermions, quarks, sorry. So since you need to fit the standard model, the masses and the CKM, like, if you take a really high value for F2, what you see is, like, you get all of the fermions to be peaked towards the IR brain, but if you do the opposite, what happens is now you need the right-handed modes to be towards the IR brain to be able to fit the standard model. So then you get these high contributions here and there. So this is at the point we're now. So this is what I wanted to tell you about. Like, we know that as I was saying, one of the most intriguing puzzles of the standard model is the flavor puzzle. We are able to solve it using a warp extra dimension, and that the most important parameter here are the fermion masses, but we don't really have an explanation to it. We were just sticking a sine function to the mass term, and we here explore the possibility of generating this dynamically. As I was saying, that this scalar field develops a web, and this gives rise to the mass term for fermions. We provide a dynamical mechanism to generate this, but also we demonstrate that it's phenomenologically viable. Like, it doesn't mess with any Ramdal-Sundrum constraint that we didn't have before, and in fact, it relaxes some of the constraints we have because the fermion profiles get diminished, not because of the change in the metric. So thanks.
Thank you very much. Questions, comments? Technically, how do you do these calculations? You look at gravity in 5 dimensions.
Mm-hmm.
Solutions of Einstein question
Yeah.
in 5 dimensions.
That would be with back reaction. Yeah.
Yeah, and to find all the overlap integrals that give you the Yukawa couplings.
Mm-hmm. Yeah.
And with that, you can find this extra contribution, for example, to the measure mixing.
Mm-hmm. Yeah. Yeah. What we do is we generate a random Yukawa matrix. Then with one of the solutions, like we have many solutions for the scalar, we fix some parameters, and then we solve it. So we have a new metric now. And then what we do is, okay, like we want to reproduce standard model, so this is fixed here. And then what we do is we find the couplings of the fermions such that they reproduce the standard model.
This is actually a fit.
Yeah, no, exactly.
The required parameters to the shape C parameters of the geometry.
Yeah. But now I get, like, the thing is, I do this this fit, but now the profiles change. Like, I don't get the same profiles. So to get the same standard model mass, I don't.
Something similar, but in a different.
Okay. So how does the pheno change once you fit the standard model? And this is given by this.
More questions or comments? I have a couple.
Yeah.
In your electroweak precision constraints, you were plotting this with the first gluon excitation.
Mm-hmm.
But I mean, the SLT parameters are just corrections to the electroweak boson propagator, so they don't know a thing about gluons. So this is because behind you have a scenario in which the masses of the modes are correlated among the gluon and the excitations of the electroweak gauge bosons. But is that completely fixed?
Yeah, the thing is, like, the mass of the gluon only depends on the metric. And for this kind of plot, I'm only using the contribution from the metric.
So that means that really what you are putting in those corrections are the modes of the electroweak gauge bosons, which are, of course, those masses correlated with the gluon.
Mm-hmm.
And then the second thing is that, well, epsilon k is a CP violating observable.
Mm-hmm.
And you are forcing the scenario to reproduce with CKM matrix. So how is CP violation encoded in this scenario?
Yeah, like,
This is a complexness.
yeah, like, the point is, like, sorry. Yeah, like, the CP parameter you still have the same as in the standard model. The thing is, now the Wilson coefficients you have are changing. So you still fit the standard model, but the thing is, like, now my Wilson coefficients, like, sorry, let me show you.
Yeah, that I understand. The thing
Yeah,
the
and-
profiles have phases which...
The C coefficients are complex.
Mm-hmm. No, sorry. The C coefficients are not complex. Yeah, the thing is now, like, you have,
Phase comes from this question.
no, from the CKM, from the mixing matrices. The point is now the profile of the fermions.
You derive the CKM after you do all of this.
Yeah, but I think, I want to say, I'm fixing the CKM, but now I get different profiles for the fermions to fix the CKM. So now how these profiles change my...
It's a common origin of CKM and those contributions.
Yeah.
No, but the question is that the origin of your complex CKM is here. Those profiles provide that.
But you are feeding.
Yeah, but I'm doing the opposite. Yeah.
You're feeding in the answer and getting it back.
Yeah. So, is it clear?
Any other comment or question? So, thank you.
Thank you. So 2 more talks to go, so please don't fall asleep already. So I would like to be talking about this work that I've been doing in collaboration with my supervisor at CSIC about cosmic neutrinos and baryon feedback. So the point is, why caring about baryon feedback? Mainly because it has a huge impact, as well as very similar on one of the neutrinos on cosmological observables. Up to now, it has been treated like a nuisance to cosmological parameters of cosmological observables. But the question we want to address is, may it bias the measurement on neutrino mass? So let me just start with a little bit of introduction of neutrino cosmology. So we will treat neutrinos as being thermal. If they are not thermal, Isabel told us how to deal with them. So they decouple very early in the universe while they're still relativistic. So they behave like radiation, while in the late universe, when the temperature drops down below their value of the mass, they start behaving like matter. But despite it, they have large thermal velocities, and as a consequence, they cannot cluster on scales that are much smaller than the free streaming length, which depends on this way on the neutrino mass. This has mainly 2 consequences on cosmological observables. One is that you have a very different halo mass function with respect to a lambda CDM cosmology, the standard one. And besides, you also have a different clustering on smaller scales, because you cannot confine neutrinos in small regions. So, unfortunately, up to now, we have only been able to find upper limits for the neutrino mass, although there are some papers recently who showed that there is a marginal preference at 1 sigma for a non-minimal neutrino mass. So here you can see that the tightest constraints that we have on neutrino mass up to now are taken by joining CMB data from Planck, here I stick to Planck 2015, and adding data from Lyman Alpha Forest. And we now know that neutrino mass, the sum of the 3 neutrino masses, is smaller than 0.12 electron volts up to 95% confidence level. So on the other hand, besides this effect, we also have baryon feedback in our universe. What do I mean by baryon feedback? Well, I mean just a set of astrophysical events, astrophysical processes, who can modify the matter distribution at the size of halos. So let's say megaparsec, tens of megaparsec scale, that are the same scales that are affected by free streaming. And so, for example, we have activity by AGM, by active galactic nuclei. We have also galactic winds produced by starburst galaxies, that are galaxies that produce lots and lots of stars per year, let's say of order 1,000 solar masses per year of stars. And also the opposite, supernova explosion. And also we remember that in the middle of galaxy clusters, there is a hot gas that emits X-rays for Bremsstrahlung radiation. Problem is that we really have few constraints on these parameters and on these processes, despite we know that there's a huge impact on cosmological observables. So what usually one does is to run cosmological simulation with both cold dark matter particles, which are treated as collisionless particles, and particles who suffer from pressure effects. And once you run your simulations, you have 2 paths you can go to. One is, I just want to reproduce my data, my clustering data, by using pure fitting functions. So basically, I take my fitting function with as many parameters as I want, they can be tens, and I just want to reproduce the clustering properties of my simulation. That's not the path we have chosen to use, but we'd rather use this baryon correction model by Schneider et al., which has 2 advantages. First, it treats the baryon feedback as a modification of what a halo of dark matter would be if it would not only have dark matter but also baryon. So it's a modification of dark matter halo properties. And also we want to introduce few parameters. In fact, we will only have 3 parameters with a well-established physical meaning. And these 3 parameters are the following. So basically, you took a threshold mass and you say, okay, my halos are halos who have mass that's above this MC have baryon gas in them, while halos which are below that mass are emptied for the mass, so there is no gas inside them. There is also this eta B parameter, which can be viewed as the ratio between the thermal velocity of the gas inside the dark matter halo and the halo escape velocity. And there is also a time evolution of the baryon feedback. So how does this impact cosmological observables, we are going to use two different observables. One is the cold dark matter plus baryon power spectrum, that tells you how much the matter is clustered in Fourier space. This is not actually a real observable because you usually observe galaxies. But still, if you are not able to disentangle the effects of baryon feedback and massive neutrinos at the matter level, you have no chance of disentangling them observing galaxies. So that's why we stick to it. We divide our mock data in 16 different redshift bins, spanning from redshift 0.5 to 2. That's approximately the range of redshift that Euclid and future missions will look at. And we also want to measure cosmic shear, weak lensing power spectrum. That is, basically, you count pairs of galaxies which are aligned. So you want to compute correlation of orientation of galaxies. And here we divide the galaxies into 3 different redshift bins. So how does baryon feedback and neutrino mass have an impact on observables? Okay, this is the ratio of the cold dark matter power spectrum with respect to a cold dark matter power spectrum without the effect. So basically here we are adding neutrino mass, and you see that increasing the neutrino mass just suppress the clustering in Fourier space. So here we have K, so you have large scales on this side and small scales on this side. You see that MC, that's the threshold mass, controls the height of the suppression. So the higher the activity of feedback, the higher MC is, the more you have suppression. Eta B controls the scales at which this suppression occurs. That means the higher the thermal velocity of your gas within the halo is, the more the suppression occurs at larger scales. And here you have the redshift evolution. The takeaway message is, whenever a line falls outside the shaded areas that represent the observational error and the theoretical error you commit on your observable, you have a detection of that parameter. This is the impact on the power spectrum, and this is the same for cosmic shear, for cosmic shear power spectrum. Here you don't have K, but you just observe angular scale, so you have a multiple. You expand in Legendre polynomials. So here you see that you are more able, you can already see that you are more able to constrain cosmological parameters using the 3D information of a power spectrum rather than 2D information like cosmic shear is, because the cosmic variance, that's the golden shaded area, it's pretty larger in the case of cosmic shear. So the question we want to address actually is, can we separate the two effects of baryon feedback and neutrino mass, and if yes, how? The idea is pretty simple. So we generate mock data. We don't run any simulation. We just generate mock data using the most powerful tools to predict the quantities that are affected by nonlinear evolution, such as HaloFit, that is this tool that can predict nonlinear power spectrum at low redshift. And we take into account baryon feedback using the baryon correction model that I previously presented to you. And then once I generate those data, I just feed them. And I just want to address 2 main questions. Can we recover the right neutrino mass, that is the input mass that I want to? That is, are we biasing our results by including both baryon feedback and neutrino mass? And how degenerate are the neutrino mass with the parameters of the baryon correction model? So we generate data for these 2 to the 4th parameters. So we have 16 different parameter set, and we fit them. And the answer to the first question is, yes, we can recover the right input neutrino mass in all the cases. These are all the runs that we have, 16 and 16 for cosmic shear. So I would like to let you notice that the error bars here are very, very small. I stress that this is not the error bar that we expect from future surveys like Euclid. This is just a totally different test, because here we are marginalizing over a series of astrophysical, cosmological, instrumental, and geometrical parameters. So the reason why the error bars in the case of clustering are much smaller than the error bars in the cosmic shear case is just because the features of the power spectrum are more easy to disentangle in the 3D information carried by the clustering information. I also want to show you a couple of counterplots in which you see that you can barely see the counterplots in the case of power spectrum because the error bars on the parameters of cosmic shear are larger. But you can see that there is actually a degeneracy between neutrino mass and the threshold mass below which you don't have gas in your halo. That's pretty interesting. While there is no such degeneracy between neutrino mass and feedback parameters in the case of power spectrum. You see that the contour plots are pretty parallel to the parameter axis. These two contour plots are pretty representative of the 16 different runs that we had. In the second part of my work, we just took into account also the so-called intrinsic alignment effect on the cosmic shear power spectrum. That is, whenever you measure cosmic shear, you're just counting pairs of galaxies that are aligned with each other. But these two galaxies must be lensed. Now, a priori, you don't know if those galaxies are lensed or not. So whenever you do a cosmic shear survey, you actually measure three different terms. That is, the cosmological signal, a signal that comes from one galaxy that is lensed and one galaxy that is not, and a signal that comes from two galaxies that are not lensed but are already aligned just because they are born in the same gravitational environment. And so the tidal gravitational field just already aligned them with each other. So you're measuring all of them, and you have to be able to model it. How do you model it? You model it by using this linear alignment model, which is governed by this parameter alpha, this parameter AIA, that can enhance or lower the signal whether this is positive or negative. And you see that the impact on it is pretty huge. It's pretty as large as the neutrino effect would be on the observables. But we see that the evolution is pretty different if we split the data into three different redshift bins like we did. So we hope that by performing a tomography, we are able to disentangle the two effects. And in fact, that's what really happens. Because you see that neutrino mass is always recovered within 1 sigma here and also here. These are just 4 different sets for low neutrino mass, high neutrino mass, and positive and negative intrinsic alignment. So not only we are able to recover the right input neutrino mass, but we are also able to recover the right input intrinsic alignment parameter. Now here I show also the contour plots that I showed you before, but comparing the two cases of with intrinsic alignment and without intrinsic alignment. It's good news that the two contour plots look pretty similar to each other. Actually, the green ones, the green contours are a little bit larger because this is expected because you have one more free parameters, and so you are adding degree of freedom to your observable. But the most important plot of these, this is another example, but the most important plot is this. So basically, we wanted to check whether neutrino mass is degenerate with the intrinsic alignment parameter. That's one of the most, that could be a problem actually. And we see that indeed there is a weak degeneracy only in this line when the intrinsic alignment is negative, which is pretty curious because when intrinsic alignment parameter is negative, you get an enhancement of the signal, while with the neutrino mass you obtain when increasing the neutrino mass, you obtain a suppression of the signal. That's pretty strange, but that's a nice result, I guess. So I think I already got to the conclusions, so baryon feedback can indeed be disentangled from neutrino mass, as long as you believe that the baryon correction model is the model that you want to account for baryon feedback. And as long as you use tomography, that's pretty important because with one single bin you're not able to disentangle the two effects. There is indeed a degeneracy between the feedback parameters themselves, but not with between neutrino mass and the feedback parameters in the case of matter clustering, while there is a degeneracy between neutrino mass and the cosmic shear and feedback parameters in cosmic shear data, and that must be taken into account in future surveys in order not to bias the measurement. And there is also a weak degeneracy between the neutrino mass and intrinsic alignment parameter, which is pretty important because the intrinsic alignment effect can enhance up to 10–20% the signal, and you don't want that to happen. So, future developments. Of course, we really marginalized over an incredible set of parameters. We didn't take into account galaxy bias. We just stick to the matter power spectrum. We didn't include cosmological parameters, and that would be pretty interesting to check whether there is a degeneracy between feedback parameters and cosmological parameters. We didn't take into account redshift space distortions that affect the shape of the power spectrum when you measure only redshift and not positions. And also, we didn't take into account the errors on the redshift that you measure. Also, we didn't run any simulations, so we didn't have any covariance metrics any realistic covariance metrics. And that would be a nice step forward for the analysis. So I think I'm done. Thank you.
Thank you very much. Questions, comments? Maybe I have one.
Mm-hmm.
This correlation that you have with your cutoff and MC for
This one.
here, yeah, among MC and neutrino mass.
Mm-hmm.
Well, I guess that your MCs you are putting it as a kind of sharp cutoff, as a step function.
It is.
So maybe
it's
that
here.
kind of correlation.
Mm-hmm.
If you include it in a smoother manner, that would be somehow reduced.
I don't know. The point is that, okay, the priors were pretty big because actually the baryon correction model originally accounts only for AGN feedback. So that's a thing that I didn't mention. But the point is that all the suppressions that you have in any baryon feedback model have this shape. So by enlarging your prior, even to unphysical parameters, you just are able to reproduce anything. So the point is that it's curious that look at for example here, the degeneracy was between m nu of 0.3 and MC of 10 to the 14, right? If I remember well. But it's not the point of the suppression is pretty similar, and so you expect a damping. But look at the scale at which this occurs. These are pretty different. So you have also to enhance eta b, or even to high values. I mean, the typical expectation value for this may be 1 for a high baryon feedback activity. So even the point is that you have also to take care of the value of your parameters that you get. For example, a test that we did before doing all this was let's generate data of matter power spectrum and shear power spectra with neutrino mass only. Then we fix the neutrino mass to the minimal value and try to fit only feedback parameters. And you see, for example, that here is the example for power spectrum with neutrino mass of 0.45 electron volts. You see that you are able to disentangle them with a delta chi-square of 1 with the only power spectrum. And you also obtain, for example, a log MC of order of 10 to the 15. That is that means that all halos of mass below 10 to the 15 solar masses are emptied of their gas. That's pretty unphysical. That's unfeasible.
Or comments or questions? But if not, thank you again. So apparently we make it to the last talk of the workshop and of the session, of course. So we now have Miguel Campos in search of right-handed neutrinos from dark matter annihilation with array telescopes. So,
Thank you. Well, hello everyone, and thanks for being here. The bold ones will remain until the end. I'm going to try to make it short, so maybe we manage to make the most of the last hour of sun. Right. So I'm going to talk about this work published here in collaboration with this gentleman here. So I'm going to start by assuming that you're all convinced about the existence of dark matter, and more than that, the existence of particle dark matter. And as I'm going to use these gamma ray telescopes, I think it's in order to introduce very briefly indirect detection of dark matter, which is based on the following assumption. In regions of the universe where you expect dark matter to be highly abundant, annihilation processes should take place that generate standard model particles like quarks, leptons, and bosons that then travel the interstellar medium and reach us converted as protons, antiprotons, electrons, positrons, neutrinos, and photons. each one of these particles can be detected in dedicated experiments. We're going to focus here in the photons and not just any kind of photon, because depending on when these photons were produced, they will generate a different spectrum. If they are produced in a primary vertex, they will generate a monochromatic line, which is a harder spectrum and has better signal discrimination. If they are produced in a secondary or tertiary vertex, then we talk about internal Bremsstrahlung, and then we generate a continuum spectrum when they are produced at the end of a cascade chain. So these are the ones that we are interested in here that produce higher rates but softer spectrum. So that's for indirect detection. About the model that or the setup that I'm going to introduce here, we're going to assume that whatever the dark matter particle is, whatever its properties, however we're considering that it's a WIMP, we're considering here that the only interaction with the visible sector is through right-handed neutrino states. When I say right-handed neutrinos, I'm talking about heavy particles in the order of giga-electron volts to tera-electron volts. We're not concerned about the details of the model. We're going to adopt a very phenomenological point of view here. But if you're wondering, one possibility, for example, is to gauge U1 by B minus L, and then you add 3 right-handed neutrinos in order to avoid anomalies. And with the right quantum numbers, these scalar particles here that will play the role of the dark matter particle can annihilate exclusively to these right-handed neutrinos. But this is just an example. We're not concerned about which model in particular, but the assumption of the dark sector communicating with the visible sector through these right-handed neutrinos. We're also going to assume then these right-handed neutrinos are going to connect with the visible sector through cis type 1 interactions, meaning these particles oscillate into active states that later have weak interactions and then decay into leptons, basically charged or neutral leptons. So first takeaway message here, or goal, which is to constrain dark matter models in which heavy right-handed neutrinos play the role of a portal with the visible sector using indirect detection techniques. In particular, gamma-ray telescopes. So a few words about these telescopes. We're going to use data coming from Fermilab, which is a per-conversion telescope, a satellite launched in 2008 with the following characteristics. It has an energy range of 20 mega-electron volts to 300 giga-electron volts, rather reduced effective area of 1 square meter, but a very wide field of view of 2.4 steroradians. Actually, it covers the whole sky in just 3 hours. So we're going to use their data coming from dwarf spheroidals, which are very small satellite galaxies orbiting our Milky Way that are expected to be composed mostly of dark matter and then presenting low backgrounds. So talking about backgrounds, well, they have to consider, or they model the background with terrestrial gamma ray bars, solar flares, and also a diffuse galactic emission and isotropic emission to account for extragalactic particles. So in contrast, we're also going to use the data coming from HESS, which is an imaging Cherenkov telescope located in Namibia, with an energy range of 200 giga-electron volts to 10 giga-electron volts, a very open effective area of 10,000 square meters, as it uses the whole atmosphere as interacting material, but a very narrow field of view of 5 degrees. So in this case, in contrast with the previous case, we're going to use our data coming from the galactic center. So on top of that, we also have to consider the events from the inner band of the galactic center, and a few more words about that in a few slides. So now to the method. The quantity in which we're interested here, as it was pointed out this morning, is the differential flux. Also, what people would like to call it the astroparticle connection, because it has a particle physics side, which is the dependency on the thermally average cross-section, the mass of the dark matter particle, and the energy spectrum, which is basically the amount of photons generated per dark matter annihilation. This energy spectrum, let me say a few more words about it. We calculated it using Pythia, and here we express it as a function of this variable x, which is the energy of the photons over the mass of the dark matter. And here we show 2 particular examples for our setup in orange and yellow for mass of the right-handed neutrino of 90 giga-electron volts and 10 giga-electron volts. And we compare it with 2 classical benchmark scenarios of indirect searches, which is dark matter going to be V bar and W plus W minus. As you can see, the spectra is sort of comparable to our particular setup. So naively, we'll expect that the limits that we can impose using this method are somehow comparable to those from these benchmark scenarios. To lower energies, we can see that the spectrum is a bit harder. And this is, for this particular example, I'm assuming that the right-handed neutrinos are mixing with the electron flavor. So how does it compare? How does it depend depending on the flavor? There is not so much variation as I show in this example. The tau spectrum is a bit harder, but they are quite comparable. And now it's the time to tell you about our last assumption in this analysis, which is the one flavor approximation, terminology borrowed from leptogenesis, which is basically that we're assuming that the right-handed neutrinos mix with with all the neutrino flavors in the same way. This is essential because this energy spectrum depends on the branching ratio. So if we assume that the mixing angle is the same, then it basically drops from the equation because it appears in the numerator and the denominator. So something that wouldn't be possible to measure in, for example, collider searches or direct detection experiments because of the mixing angles are quite small. We expect them to be quite small. In this case, doesn't play a huge role. So coming back to the differential flux, in the astrophysics side, we have the information encoding the so-called J factor, which is simply the integral over the solid angle over the line of sight of the square of the dark matter density, which is somehow controversial because of the cusp core problem. We don't know exactly what is the exact profile for smaller values of the distance of the galactic center. However, we're going to adopt here the Navarro-Frank-White profile for being the one that both collaboration use. And they claim that the J factors actually don't depend much about these values, on these values. So a few more words about the sources. The J factors for the dwarf spheroidals are 10 to the 19. And as I already mentioned, they lack non-thermal astrophysical processes, then producing low backgrounds. In comparison, the galactic center has J factors that are 3 orders of magnitude bigger. However, the gamma ray emission from the non-thermal processes makes a bright background. So for their analysis, basically, they cover the whole inner band around 0.6 degrees and just take into account a ring surrounding the center. So the data set, well, it's 6 years observation of dark spheroidals and 10 years observation of the galactic center. We perform a joint likelihood analysis in order to account for the particular uncertainties from these J factors using GAMLike, this code developed by Christoph Veniga, part of DarkBit. And well, our goal then is to impose limits on the thermally average cross-section as a function of the mass of the dark matter and the mass of the right-handed neutrino. So second takeaway message, basically the experiments give us the differential flux associated with a J factor for each source. And as for a particular model, we can calculate we can calculate the differential, the energy spectrum, sorry. Then we can impose constraints on this thermally average cross-section as a function of the dark matter mass, which is what I show here. Our results are for Fermilat are in blue, and those coming from Hess are in red. As you can see, and as I already predicted, they are quite complementary, around 500 gigaelectron volts. One takes over the other. These are for 95% confidence level, and I show here in solid line, dash line, and dot dash line the result for 3 values of the right-handed neutrino mass. Last takeaway message, and this is for annihilation into into electron flavor. Into tau, it's a bit stronger, as already predicted again. So last takeaway message, if we assume that the dark matter particle is a WIMP and is thermally produced, and it annihilates exclusively into these right-handed neutrinos, then we can rule out masses of 200 gigaelectron volts for this WIMP, depending on the mass of the right-handed neutrino, of course. And so I already reached my conclusions. I mentioned that I was going to be quick. So we have investigated one possible role that additional neutrino states can play in particular the portal case, not the dark matter candidate as sometimes is considered. And we conclude that despite experimentally challenging small mixing angles, interesting limits can be imposed using indirect detection. In particular, using public data available by Fermilab and Hess, we can rule out masses up to 200 gigaelectron volts for a thermally produced dark matter. Thank you.
Thank you very much. Questions, comments? That means that the portal must be heavier than the portal.
Heavier than the dark matter particle?
Then,
Not necessarily, so it depends.
then 200, you said.
Yeah. Right. So, of course, when it's 1 tera-electron volt, then the limits start from 1 tera-electron volt. So, yeah, in that case, yes.
More questions, comments?
Yes. Please.
Who is the beta for the background feature?
It's Fanco, but it's a modified version of the Starry Night. So, very non-physical. I changed the background for the Planck data. Yeah, I modified it, yes. Any physical questions?
Fake painting,
Yeah.
not fake news. Well, it's not, it's time.
Thank you.
I must say some things are required for agradecimientos, as we say in Spanish. So we want to thank our sponsors, Generalitat Valenciana, who financed the meeting to a large extent, the Ministry of Science, through our Excellence Grant of our Institute, Severo Ochoa Grant. Our institute itself also helped us, and very important for us was the support of Delegación of CSIC. This is like the local Max Planck delegation in Valencia, Max Planck meaning CSIC. They provided us this beautiful setting to hold our meeting. I'm thankful to the chief, my friend José Pío Beltrán, and also the people from La Casa de la Ciencia, especially Mariluz and Julio, who helped a lot. And of course, the help of our scientific secretary. Mari was here, Christoph Ternes, Salva Centelles, and others. I think also Ivania helped. And on behalf of all the co-organizers, Martin Hirsch, Sergio Pastor, Rahul Srivastava, Mariam Tortola, Avelino Vicente, who were all very patient with all that we have to do for the bureaucracy to put such a small thing working. I think they were essential. Without joint work, we would not have been able to do it. And of course, on behalf of them, I want to thank all the speakers who came for their good talks and all the participants. And the last thing is, Valencia is not only famous for the physics, for the good physics, but also it is the first Erasmus destination in Europe. So I hope you have a chance in the last nights, if you stay around, to discover why. Thank you very much.